injection panel is used to supply clean gas to the turbine and the compressor dry gas seal. Due to the high speeds required, the compressor impeller is driven by a motor through a step-up gearbox. It compresses the CO2 from 90 bars to 210 bars. Next, the CO2 passes through the recuperator, where it is preheated using residual heat from the turbine exhaust. The two heaters used in the system have different purposes. The first stage heater serves as a replacement for the recuperator during startup when recuperation is absent. The second stage heater is a stand-in for the external heat source in an actual installation, which could be concentrated solar heat from a solar tower, a coal-fired boiler, or exhaust heat from a gas turbine in the case of a waste heat recovery system. The combined heat addition from both stages is about 141 kilowatts. The density of the high-pressure CO2 drops drastically during the process of heat addition, from 461 kilograms per meter cube to 132 kilograms per meter cube. CO2 at 210 bars and 535 degrees Celsius enters the turbo generator to generate power. The temperature drop across the turbine in an SCO2-based system is smaller than in conventional systems. The turbine exhaust is therefore at low pressure but at a fairly high temperature of about 470 degrees Celsius. Instead of rejecting the entirety of this high residual thermal energy to the ambient, some of it is recovered by passing it through the hot side of the recuperator to exchange heat with the low temperature CO2 from the compressor discharge. The low pressure CO2, now at an intermediate temperature, finally rejects heat to ambient in a gas cooler using water as the cooling medium. This CO2 is again fed to the compressor suction and the cycle repeats. The realization of SCO2 technology comes with a lot of hurdles. Compact turbomachinery is one of the key challenges, due to its very high operating speeds ranging from 60,000 to 150,000 RPM. Various configurations have been explored, including standalone gearboxes with flexible couplings as well as integrated gearboxes. Rotordynamic concerns, sealing, and very tight manufacturing tolerances all make it an engineering nightmare to realize the technology at small scales. Another major challenge in the SCO2 turbomachinery is to maintain the dry gas seal temperature of 160 degrees Celsius as specified by the DGS manufacturer. The dry gas seal is in close proximity to the heat source, so numerous cooling techniques have been incorporated into the turbomachinery to maintain the DGS temperature below 150 degrees Celsius. Rotor dynamics and structural integrity of the shaft are critical in high-speed applications. Since the machine operates beyond its second critical speed, several iterations of design and simulation have been performed to optimize the shaft dimensions and reduce the force on bearings at critical speeds and ensure the safe and continuous operation of the turbomachinery. The impeller of a centrifugal compressor for the test loop is no bigger than twice the size of a 10 rupee coin and spins at 60,000 to 80,000 revolutions per minute. The design and manufacture of such small impellers have been a challenge. In addition, the non-availability of suitable generators and motors has necessitated the indigenous development of high-speed switched reluctance motors and generators for the test loop. Another major challenge in the development of the SCO2 cycle is the high-pressure, high-temperature heat exchangers. Printed circuit heat exchangers or PCHEs offer very high cooling capacities in a small footprint. They are also highly efficient compared to conventional shell and tube heat exchangers. A PCHE comprises alternately stacked hot and cold plates. The stack is diffusion bonded in a vacuum furnace. Diffusion bonding of the stack is followed by welding of headers and diffusion plates to create entry and exit manifolds for hot and cold fluid streams. The thermohydraulic design of the channels is an important parameter deciding the performance of the PCHE. The channels are arranged in a manner that ensures counterflow heat transfer between hot and cold fluid streams. IISc has indigenously developed a 200-ton vacuum hot press to manufacture these printed circuit heat exchangers. A patent has been granted to IISc for a novel method of manufacturing heat exchangers. A number of instrumentation and control techniques are also being devised to allow a stable operation of SCO2 systems, particularly for waste heat recovery and concentrated solar power applications where source temperature can vary significantly. IISc Bangalore along with Triveni Turbines is working on a host of applications that could benefit from the utilization of SCO2 technology. These include waste heat recovery for cement and steel industries and bottoming cycles for gas turbines. In this regard, a number of patents have been filed, such as a new thermodynamic cycle for waste heat recovery which performed 12 to 15% better in terms of output power than the current SCO2 cycle for waste heat recovery. IISc and its partners are proud to be among the pioneers of SCO2 power generation, which holds great potential as one of the pivotal technologies in the global shift towards sustainable power.